class today. Okay, today I will finish off the effectiveness NTU method, and I know that many of you already proceed to design your heat exchanger. Okay, and then Junti is asking how we can decide the number of pass and tubes. If there's no input from icon, then you have to decide on your own. Then after that, you can check the size of the heat exchanger, whether it can fulfill the total surface area or not. I believe maybe you can get the surface area in the icon for the heat exchanger. Okay, and then Bing Sun. Okay. For the number of shell and tubes, okay, yeah, in the appendix or in the textbook, it may consist up to 2 shells only. You can refer to any others reference book as well. Okay, you may refer to any others reference book, and then you actually, if you have a high power output, okay, maybe you can consider to have 2 parallel heat exchanger instead of 1. Okay, it is allowable to design 2 in parallel in order to gather that heat capacity. Okay, so if you think you can actually increase the number of tubes in order to increase the surface area. Okay, all right. Is there any other questions before I proceed? Because the deadline for the submission will be on 18 August. Okay, you have about 1 week plus to complete. I guess you all have completed the thermal part, isn't it? Since the problem statement has been released earlier. Okay. There's no any maximum input of mass flow rate. Okay, you need to assume. Okay, you need to do the assumptions yourself by putting, maybe you can put some references. You can refer to the power plants, see roughly, okay, for the condenser, okay, what would be the mass flow rate of the cooling water use, or usually because the power output, I guess you actually know it from the steam turbine. Okay, so for the cold flood, you need to assume yourself. After the design, maybe you need to repeat your design to see, to get the reasonable value. What do I mean? Like reasonable value is you can compare in the website the common or the commercial type of shell and tube heat exchanger. Usually, its surface area is how much, a number of shell is how much, or number of tubes is how much. Okay, so in order to get comparison, and then you can check usually what would be the length of the tube, what would be the diameter of the tube. Okay, what would be the diameter of the whole heat exchanger. Okay, so I believe you can get this information easily in the website. Then you can do the comparison on your own design and their design. If you found that the value that you got is very, very much different or out of the range of the commercial type of heat exchanger available in the market, then you might need to consider again to do the recalculations. Maybe you need to assume the other value of mass flow rate, or maybe any other factors that could affect your design. Okay, so this is some type of hints that you might able to come up with the proper design of your heat exchanger. Doesn't matter, it is just a integrated project, and then you know that how would you design the heat exchanger, by what factor you have to consider. Okay, all right, I think without further ado, you can still WhatsApp me or email me if you have any questions on the integrated project. Okay, I will reply as soon as possible. Okay, all right. So yeah, I need to proceed. Okay, so after the effectiveness NTU method, I will summarize the assessment of a process heat transfer. and then how far we have completed the number of assessment and how many assessment that remaining, and we have to complete it within this 2 weeks time. Okay, right now is the end of week 10 already, and then I believe all of you already aware of your EA extended assignment, which is actually scheduled on 30th of August, 3 p.m. until 31st August, 2:59 p.m. You have to upload. Okay, upload in Ulearn 1 day time. I hope that this time you all do not facing any internet issue or uploading problem. Okay, so that everybody can submit and upload in Ulearn within this 24 hours time. Okay, so without further ado, we come to the last topic on the heat exchanger, which is effectiveness NTU method. Okay, so in analysis of heat exchanger, basically we have two methods over here. The first one you all already learned. I believe many of you already proceed with the design by using log mean temperature difference method. But it is okay if you want to use effectiveness NTU method also can. If you want to proceed to LMTD also can. No need to have two method design. No need, because eventually you will get the more or less same answer if let's say you want to get the um, surface area. Okay, or if you want to get the outlet temperature, definitely you need to get you need to use effectiveness NTU method. Then finally, we will have a very small topic on selection of heat exchangers, some criteria that you need to think of. Maybe some of you already proceed to read the notes over here, but it's okay. I would just explain further. Maybe it will clear your doubt when you do the self-studying. Okay. So effectiveness NTU method. A second kind of problem encountered in heat exchanger analysis is the determination of the heat transfer rate as well as the outlet temperatures of the hot and cold fluids for prescribed fluid mass flow rate, meaning that the mass flow rate of the fluid has to be known. Okay, as well as the inlet temperature. These are the two criteria. So mass flow rate and inlet temperature has to be there for the cold fluid and hot fluid. Okay, and then actually you need to analyze the heat transfer rate and outlet temperature by using the effectiveness NTU method. This is the general information on using the effectiveness NTU method. But it can be like maybe some extra temperature given, 3 out of 4 temperatures are given. If in this case, you can have option either using effectiveness NTU or LMTD method. Okay. And then when the type and size of the heat exchanger are specified, usually the surface area will be given, and then the type of the heat exchanger also will be given. Okay, so your job is just to determine the outlet temperatures and then also the heat transfer rate. For the LMTD method, all 4 temperatures have to be there. Okay, don't forget for LMTD, you need to calculate delta T1 and delta T2. Okay, and then you need to get the P and R value. All 4 temperatures have to be there. Okay, then you determine the size. What would be the surface area? Okay, that finally you need to design in order to achieve that particular rate of heat transfer. Okay, okay, the heat transfer surface area of the heat exchanger in this case is known. Okay, but the outlet temperatures are not. This is the common case, general case of the problem whereby you can use the effectiveness NTU to answer the questions. Here, the task is to determine the heat transfer performance of a specific heat exchanger, or to determine if the heat exchanger available will do the job or not, whether it can cool that fluid from particular temperature to the targeted temperature. Okay, you want to see whether by using this heat exchanger, whereby we know the size of the heat exchanger, whether it can achieve the targeted outlet temperatures or not. Okay, so by knowing the size and type, so in the other way around. Okay, so this is the general, the common case or the common criteria whereby you have to use the effectiveness NTU to resolve the problem. Okay, so let us look at this slide. In fact, effectiveness NTU method is actually very simple, the concept. Okay, you can look at here. Okay, the effectiveness, okay, is the actual heat transfer rate divided by maximum possible heat transfer rate, meaning that this one is ideal case whereby the heat exchanger could not achieve, okay, maximum possible, the possibility only, and then the actual heat transfer rate. Okay, then you will get the effectiveness. So in heat exchanger chapter, this one is not emissivity, students. So this one, epsilon here in radiation heat transfer, we define it as an emissivity. But in heat exchanger, it is effectiveness. So the definition of effectiveness is very simple and straightforward. The actual heat transfer rate divided by maximum possible heat transfer rate, whereby the heat exchanger operate at 8 ideal case. Okay, and the actual heat transfer rate from energy balance, this is not new to you all. Okay, so it is CC. Okay, CC is MCCPC. Okay, the capacity rate, and either you can use MCCPC over here. Okay, TC out minus TC in, because the temperature outlet of the cold stream is always higher than the inlet because the cold stream being heated up at the end. And it is also equals to the heat transfer rate for the hot stream. CH, capital letter C, H is MCCPH. Okay, so I think a mistake over here. This one is MH. MHCPH. Okay, all right. Then after that, you will have TH in minus TH out. Okay, so TH in is always higher than TH out because this hot stream being cooled down after exchange the heat with the cold stream. Okay, and then there will be always the maximum delta T. Okay, whereby it is the TH in minus TC in. This one is always. Okay, the hot fluid inlet temperature minus the cold fluid inlet temperature will be always delta T max in a heat exchanger. Okay, because their difference is the highest. Okay, and then here we can count or we can calculate the maximum possible heat transfer rate. Okay, Q max. Okay, okay, Q max is actually just the delta T max. This one is delta T max isn't TH in minus TC in. Okay, delta T max times C mean. Okay, what is C mean? C mean is the smaller CH or CC, meaning that first, when you come across this kind of effectiveness NTU method problem, you need to calculate CH and CC. Okay, so you see which one is smaller. Okay, so the smaller one will be the C mean. Okay, so you can get the Q max easily, okay, by just multiplying the delta T max with C mean. Okay, so this is the equation, very important equations to get the Q max. Okay, Q easily get it from here, MCP delta T from the cold side or from the hot side. Okay, Q max is a C mean delta T max, or the delta T max is defined as TH in minus TC in. Okay, the maximum possible, no, the maximum difference of temperature, okay, in a heat exchanger. So let us look at the examples how you can determine the Q max. Let's say this is typical type of effectiveness NTU method, the analysis of heat exchanger by using effectiveness NTU method, whereby the outlet temperatures are not given, you see, you do not know. But the mass flow rate is given for the hot and inlet temperature and CP value as well. Okay. For the cold stream side, also the same. The TC in is given, and then MC, CPC are given. Okay, so the very first step of the effectiveness NTU method is you determine the CC and CH. So for this case, CC is MCCPC is 104.5. Okay, CH is 92 kilowatt. per degree C or per Kelvin. So which one is smaller? Yes, 92. So this one straight away will become C min. And then delta T max is always TH in 130 minus 20. Then you will get 110. Eventually, you can get Q max, whereby Q max is C min times delta T max. Just this one, multiply these two. Okay. Any questions, students? In order to get the effectiveness, you have the actual heat transfer rate and then how you get the Q max. Okay, you have to understand this situation or this condition, especially you need to understand the delta T max equation and how you would able to calculate the Q max. Okay, so it's just simply C min times delta T max, and the C min is the smaller CH or CC. Okay, this is the definition of all this term. Any questions before we move further? Okay, if no questions, then I move to the next slides. Okay, so this slide is just a sample for you all to calculate the Qmax, and then it's actually the upper limit of a heat exchanger in a heat transfer, whereby you see the question itself, we read it first. Okay, cold water enters a counterflow heat exchanger at 10 degrees C at a rate of 8 kilogram per second, where it is heated by a hot water stream that enters the heat exchanger at 70 degrees C at the rate of 2 kilogram per second. So very typical, the inlet temperature for the cold stream and hot stream are given, and then the mass flow rates are given. And then the CP for both stream is 4.18. That means the maximum heat transfer rate and outlet temperature of the cold and hot water stream for this limiting case. Why we call it as a limiting case? Because you calculate the outlet temperature and also the TH out by using the Qmax value. Okay? In fact, if you want to get the real temperature outlets, you need to use the Q. How to get the Q? Q is just the effectiveness times Qmax, because you have effectiveness equals to Q divided by Qmax. Okay, that's why this is a very special example whereby you need to calculate the outlet temperature by using Qmax value. Okay, so this is the questions. That's why it's saying that it's a limiting case, because we calculate the outlet temperature by using the Qmax value instead of by using the Q value. Okay, so let us move to the whiteboard. I would like to share my screen. Okay, so it's back to here. So upper limit for the heat exchanger. So as usual, you can draw the picture. So counterflow heat exchanger, it will be like this. Okay, so this is counterflow. Okay, so you have a TC in. So for double pipe counterflow, doesn't matter the stream, the hot stream or cold stream under which part. Okay, it's okay, no worry, because it will not affect your calculations. So TC in, it's 10 degrees C. Okay, the MC is 8 kilogram per second, and then you have CPC, it's equals to 4.18 kilojoule per kg. Okay, then you have also, this one is hot water, and this one is cold water. Okay, sorry, this one is cold water, because TC, And then this one is hot water. Okay, and then you have TH in equals to 70 degrees C, MC and CPC. They are having the same CP value because it is water. Okay. Right now, the question is asking you to calculate the TC out and then the TH out under Qmax condition. Okay, under Qmax condition. So in fact, this question is very simple and straightforward. First, you calculate the Qmax, okay, and then the Q equals to Qmax equals to Q and is equals to MCCPC, TC out minus TC in, and that is also equals to MH TH in minus TH out. Okay, so there will be the common or the first step, the very first step that you need to start with under the effectiveness NTU method is to determine C mean. Okay, how? You need to get the CH equals to MH CPH. It is equals to 2 kilogram per second times 4.18. So you will get, okay, so this one is degree C, sorry. This one is degree C. Okay, then you need to get the CC equals to MC CPC. So it is equals to 33.4 kilowatt per degree C. Okay, then after that, you need to identify which one is CMIN. So by looking at this two, this one is CMIN. So this one is CMIN. So CMIN is equals to 8.36 kilowatt per degree C. Okay, after you know C mean, you can easily get Q max, whereby it is equals to C mean times delta T max, isn't it? So it is equal to C mean delta T max. You have to remember TH in minus TC in. It's always this. This one will always experience the highest temperature change, the inlet temperature, the difference of the inlet temperature between the cold and hot fluid stream. Okay, then you do the substitution, and then TH in as 70 minus 10, then you will get 501.6 kilowatt. Okay, all right. So after you get this one, okay, after you get the Q max, okay, we are using Q max as a Q to calculate the TH out and also the TC out. Okay, so Q equals to, okay, you can strip away CC, okay, as TC out minus TC in. Okay, then you can rearrange the equations to get the C out. Okay, so TC out equals to Q divided by CC plus TC in. Okay, then this Q is equal to Q max. Okay, so eventually by substitution, you can get this value is equals to 25 degrees C. So you just put all the value in it. Okay, just put all the value in it, then you will get the value. Similarly, okay, Q equals to CH, TH in minus TH out. Okay, I hope you all will not confuse with which one in, which one out. Okay, so the hot stream is being cooled down. Of course, the inlet will be higher than the outlet. The cold stream is always being heated up. That's why TC out is always higher than TC in. So eventually, you will get your TH out. Is it equals to TH in minus Q equals to CH. Then you will get the Q 10 degrees C. Okay. Any questions, students? I'd like to hear. Any questions on this limiting case? So in fact, you can just use this equation MCP delta T and then Qmax colorations equation. Calculate CH, CC, and then you will get C min, okay, the lower value. Then after that, calculate the Qmax, okay. Then eventually you can get the outlet temperature of the hot stream and cold stream. Okay. All right. So it's very simple and straightforward, isn't it, students? But we haven't go to the real case. This is just the limiting case. Okay. So students, there is a discussion slides over here regarding on this example. We look at it. Okay. Hot water is cold to the limit of 10 degrees C. So meaning that, okay, this hot water, so TH out, it's close to the 10 degrees C. Okay, this 10 degrees C is actually the inlet temperature of the cold stream. So it's cold, it's being cold to the limit of 10 degrees C, the inlet of the cold stream already. But however, why the cold water is only heated up to 25 degrees C only? The hot stream can be cold from 70 to 10. But why the cold stream is only can heat it up from 10 to 25? Any any logical thinking from you all? Yes, definitely, Ravindraj. It's because of the reason is very simple. It's because of the mass flow rate of the hot water is 1/4 of that of the cold water. So you can see here, the mass flow rate of the cold water is 8 kg per second, 4 times higher than the hot water. Okay, of course, the hot water can be cold to the 10 degrees C, but the cold water cannot be heated up to 70 degrees C. It's impossible. Okay, if you do not agree with this, you can perform calculation. If you want the hot water, if you want the cold water to heat up until 70 degrees C, it will require the temperature of hot water to drop to minus 100 degrees C. It is impossible. Okay, so it is impossible if we want to heat up the cold water until 70 degrees C, similar with the inlet temperature of the hot water. Okay, so you can try yourself. Okay, you will really get hot water need to drop to minus 170 degrees C. Okay, I share my screen. You can actually perform the calculation to prove that. Because you are an engineer, always you want to prove. Do not just listen to the people saying this and saying that. You have to see yourself and prove yourself. Okay, whether it is truly dropped to now minus 100 degrees C or not. Just now we mentioned, okay, if let's say you can calculate the Q, okay, so let's say the TH in right now, T cold, TC in right now is 10 degrees C, and then I want to heat it up to 70 degrees C. So you can calculate the Q needed. Okay, MCCPC PC out minus TC in. Okay, it is equals to, isn't it? Okay, so this amount of heat transfer rate is required for the MHCPH, okay, TH in minus TH out. Okay, so here you can get your TH out. Yeah. Q divided by MHCPH. Then eventually you can get minus 170 degrees C. You substitute the value and see, students. So this Q is here. So it is impossible. Okay, it is impossible. That's why the cold stream is only able to heat up to 25 degrees C because of this limiting case. Okay, if I want to heat up the cold stream from 10 degrees C to 70 degrees C, I need this huge amount of heat. If I need this huge amount of heat, you can see that the heat TH out eventually will become minus 170 degrees C. Okay, agree? Any one of you have proved this one by substituting all the value in it? Okay, any one of you prove that it is minus 170 degrees C? Or you all still proceed with the calculations? So students is always, you have to verify. So as an engineer in future time, okay, so you will need to always verify, okay, compare, okay. So have more critical thinking compared to the others, okay, to verify the things on your own, okay. So it is minus 170. Is any one of you have proved this one? Okay, that's good. So this is a very special case. So it's under limiting condition and whereby we only able to to heat up the cold stream from 10 degrees C to 25 degrees C, but the hot stream experience the largest change of the temperature from 70 to 10. It is because the mass flow rate. Okay. Therefore, heat transfer in a heat exchanger reach its maximum value when the fluid with a smaller heat capacity rate experience the maximum temperature change. This one exactly explain, okay, what I have explained just now. Okay, so this is the examples of the limiting case. Okay, all right. Any questions, students? Before we proceed further to analyze the effectiveness NTU method? If no questions, then I will proceed. Okay. The determination of Qmax require the availability of the inlet temperature of the hot and cold fluids and their mass flow rates. Once the effectiveness of the heat exchanger is known, the actual heat transfer rate can be determined from this one. Okay, so you just rearrange the equation, then you will get the Q. Okay, so in fact, if you want to calculate the effectiveness, okay, when you know the inlet and outlet temperature, then you can actually get the effectiveness. Okay, if CC equals to C min, meaning that the Q equals to this one can be MCCPC from the cold stream side, and then this one Q max because this one is C min, and then this is TH in minus TC in. Okay, so you can easily okay, get the effectiveness if the temperatures are known. Okay. Or if the CH is C mean, similarly, the Q itself you can calculate from the hot stream side, MH THE minus THL, and then divided by this one is become C mean. Okay, the temperature change of the heat exchanger will eventually become the effectiveness. Okay, all right. Usually we will not calculate it in this way because the outlet temperature usually is unknown. Okay, so usually is unknown. Okay, so we have other ways. Okay, we have other ways. So we will introduce the NTU right now. So why we call it as the effectiveness NTU? It is actually explained in the following slides. Okay, the effectiveness of a heat exchanger, the heat transfer rate can be determined without knowing the outlet temperature of the flux. Okay, the effectiveness of a heat exchanger depends on the geometry, okay, of the heat exchanger as well as the flow geometry. You see, let's say for example, this is the parallel flow double pipe heat exchanger. Without knowing the temperatures, you can eventually get the effectiveness. So this is the correlations used to determine the effectiveness of the parallel flow heat exchanger. So meaning that different type of heat exchanger will have different correlation. Okay. So this one is only for parallel flow. Okay. This one is only for parallel flow. All right. Later on, we will see a table showing different correlation for different type of heat exchanger, meaning that the effectiveness of a heat exchanger, it can be determined without knowing the outlet temperatures of the fluid. Okay. All right. And then we have a new terms over here whereby the NTU is coming in. Okay. So NTU is defined in equation 39. Okay. Yes, effectiveness is impossible to achieve 100%. No, there's no, heat exchanger can have the 100% efficiency. No. Okay. The quantity is called number of transfer unit NTU. So NTU, the definition is number of transfer unit. Okay. So NTU is number of transfer unit, and that it is defined as UAS divided by C mean. Okay, UAS divided by C mean. U is the overall heat transfer coefficient that you learned it in the previous class. C mean just now I introduced already, and AS is the surface area. Okay, all right. So you can define the NTU already. This is the correlation. Okay. All right. For specific value U and C mean, the value of NTU is a measure of surface area. You see, NTU is a function of surface area, isn't it? You see. All right. Thus, the larger the NTU, the larger the heat exchanger, meaning that the size of the heat exchanger will be higher if the NTU value is higher. Okay. So before we proceed to understand the relationship between the effectiveness and also the NTU, we need to know a new term of capacity ratio. Okay, so for the effectiveness NTU method kind of problem, first you need to get the C mean, then C max, then eventually you need to get also the capacity ratio. Why? Because in order to get the effectiveness, okay, you need to know the NTU and you need to know the capacity ratio. So you can go to the previous slides, okay. You need to know the NTU. This one is NTU. This one is capacity ratio. This is small letter of C. This is actually NTU. Okay, so meaning that the effectiveness, in order to get the effectiveness of the heat exchanger, you must know the NTU value and you must know the C. NTU is the number of transfer unit, is a function of surface area, and it is it can be defined as UAS divided by C min. Okay, this is how we get this relationship. Okay, sometimes the question is asking you to calculate the Q. So in order to calculate the Q, you need to know the effectiveness and Q max. Q max usually will be easily determined. Only the effectiveness. So in order to get the effectiveness, of course, you need to know the NTU. Okay, NTU you can determine by using this equation. Okay, so there is a correlation. Of course, the capacity ratio is there in the equations. Okay, so this is the relationship between effectiveness, NTU, and also the capacity ratio. They are interrelated. And this NTU, you can get the surface area. And by knowing the effectiveness, in fact, you can get the Q value. Okay, this is how they play around with. Sometimes the question is asking you to calculate the Q, and sometimes the question is asking you to determine the surface area or the length of the pipe. So meaning that the calculation will be on the other way around. Okay, you need to calculate the effectiveness. After that, you need to get the NTU. Then after that, you will only able to get the surface area. This is how this relationship play around. Okay, effectiveness, NTU, surface area. Okay, number of transfer unit. So for this case, you do not need to know the outlet temperature at all. So meaning that without knowing the outlet temperature, I can easily get the surface area, the size of the heat exchanger. Okay. Eventually, of course, you can use your Q value to determine the outlet temperature. No problem. So meaning that whether you can you can check whether this exchanger is able to perform the job or not, is able to achieve your target outlet temperature or not. Okay. So this is the ultimate goal of using effectiveness NTU method. LNTD method is not the same. Okay, it's all four temperatures are given. You need to determine the size. What will be the heat transfer area that you need in order to achieve that particular temperature change? Okay, so this is the other way around effectiveness NTU method. Okay, so just now I mentioned you can have the relationship. You can see, okay, different type of heat exchanger type. You will have different equation to calculate your effectiveness. Okay, like for example, parallel flow, counter flow. Okay, one shell, two four tube passes, and then end shell, and then also the cross flow. You will have different equation to use, or you can get the NTU value by using the correlation as well. Okay, so these are all the equation for respective type of heat exchanger. Either you have to you want to calculate the NTU, or you want to determine the effectiveness. Okay, so these two tables can be used. And then eventually, if you don't want to use the equation, you can use the graph. Okay, similar with the way that you get the F value, but this one will be a bit different. Okay, so you need to know the C. This is capacity ratio, isn't it? Don't forget we have effectiveness is a function of NTU and also capacity ratio. By knowing the capacity ratio, by knowing the NTU, let's say the NTU is 2, the capacity ratio is 0.5, then you just read it from here. Then you get the effectiveness is 0.6 something, 122. Okay, this one is actually sometimes I would prefer the student to use the equation because you can see some value, the line is actually overlapping. For example, this side, it's very difficult to read. Okay, so if you get the lower NTU, okay, or lower capacity ratio, it will fall under this range. So it's really difficult to read the effectiveness value. If in this case, you need to automatically go to the equation, even though the calculation is needed, okay, but it will get more accurate result compare you read it from the graph. I will accept both if there's a clear remarcations over here, okay, like for example, if it's a two shell multiple tubes, let's say the NTU is 3, okay, the capacity ratio is 0.5, this line, then you can read it clearly over here. Then I will accept, no problem. If for the range, this one below 1, whereby you have difficulties to read the value, then I will check your answer, see whether it's accurate or not, or too far from the calculated value by using the table. Okay. So on the other way around, you can get the NTU if the effectiveness value is known. Like for example, okay, I go to the counterflow heat exchanger. If I know the efficiency is 60 and the capacity ratio is 1, I can easily read from here and then here. Then the NTU is about 1.7, some sort like that. Okay. So it can be the other way around. You read the effectiveness by knowing the NTU and capacity ratio, or you read the NTU by knowing the effectiveness and capacity ratio. Okay? Is that clear, students? How you can get the effectiveness or NTU value from the chart and also the table. Any questions, students? If no questions, can I proceed, student? Just for a while to do the summary before, then we will have a break. Then we go to, for two examples. Then we officially end this chapter already. Okay, so this we have for cross flow as well. One fluid mix. Okay, both fluid are mixed. One fluid mix and the other are mixed. Okay. All right, just a simple analysis over here. Okay, so for a specific NTU and capacity ratio, the counter flow heat exchanger has the highest effectiveness and the parallel flow is the lowest. So they take out, okay, one line from these three heat exchanger, parallel flow, counter flow, and also the cross flow with both fluid and mixed. They just take one line, okay, under the same capacity ratio one. They want to compare which one under the same capacity ratio, okay, which type of heat exchanger having the highest effectiveness, which is falls under counter flow. Okay, so this is a kind of analysis. Maybe you have some doubt in your mind. I want to know. Okay, in fact, I see many lines, but I do not know which one is actually giving me the highest effectiveness if the capacity ratio is the same. So actually, you can deduce many information from the chart, or by comparing all these different kind of type of heat exchanger in order to design which type of heat exchanger you want to use. Okay, so under this analysis, okay, so it's shown counterflow is the highest, and then you can see if the NTU is below 1, so the effectiveness are more or less the same for these three different type of heat exchanger. That's why it is important to know the size or the NTU and also the capacity ratio. Okay, so meaning that if my NTU is about 0.5, I know that these three type of heat exchanger giving me the same efficiency, then I will choose the one with the lower cost, definitely, because they are performing the same. Okay, then if my NTU is about 2, definitely I will choose the counter flow. Okay, if I want to get the higher efficiency and I do not have any limitation on the budget. If you have any limitation on the budget, you can do some calculation, the costing. Maybe you will choose the cross flow in the middle one in order to gather the cost. Okay. And then sometime maybe you think that, okay, the efficiency is a function of NTU, but you can see for parallel after 2, okay, after NTU 2, okay, if you increase the surface area, meaning that if you use bigger size, larger size of heat exchanger, you think if larger size the efficiency will be higher, but in fact it is not. You see, it is not. You just waste your money to get bigger size of heat exchanger. Okay. So that's why all this chart, as I mentioned just now, you can get many informations. But just whether you know how to do the analysis or not, that's important, students. So I always keep emphasize you will be the engineer in future. You have to see something others people cannot see from the chart. You have to do the analysis on your own. Okay. Similarly, for cross flow and counter flow, let's say I increase from NTU2 to NTU4. I thought I can increase the efficiency from zero point 0.6 to zero point 0.9, but in fact, it is not. There's just experience a very minimum change of or minimum increment of efficiency, but you increase the size until the NTU become 4, let's say for example, which is not worth at all. Meaning that the bigger size of the heat exchanger, you have to pay more, involve more costs. So in one day you work in the company, they will always talk about costing. Okay, save costs, save costs. Okay, so that's why you need to do the comparison calculation. Like for example, let's say I use this one, what will be the heat exchanger rate? And then if I choose the cross flow heat, what will be the heat exchanger rate? Heat exchange rate. So you need to do the complete comparison and analysis. Okay, you need to proceed or include something that maybe other peoples will not be able to think of. Okay, in order to show your value to that particular company or to that particular institutions. Okay, so this is some kind of analysis skill. Don't worry, you are in first year, so another 3 years coming on, whereby you all will involve in more engineering subject. Then you all will be able to, see more and then analyze more. Okay. Any questions? Okay, so you can read over here. In fact, what I'm saying just now is actually from here. Okay, the value of effectiveness range from 0 to 1 is increased rapidly with NTU for small value, but rather slowly on for a large value. So here increase rapidly, but after that, after 2, it's actually slow down the effectiveness. Okay, and then okay, here. Therefore, the use of heat exchanger with a large value and thus a large size of heat exchanger cannot be justified economically, since a large increase in NTU in this case corresponding to a very small increase in effectiveness only. Okay? For a given NTU and the capacity ratio, you need to compare apple to apple. So this one is apple to apple, all having the same C, okay, having the same NTU, okay. Always comparison have to be apple to apple, okay. Then the highest one is a cross flow, the lowest one is parallel. This is a good information once you want to design whether the flow arrangement of your heat exchanger. The effectiveness of a heat exchanger is independent of the capacity ratio for NTU value less than 0.3 here. As I mentioned just now, lower value is all the same. All the same. Okay? So a quick summary over here before we go for a break. Okay? When all the inlet and outlet temperature are specified, the size of the heat exchanger can be easily determined by using LMTD method. Okay? If the question do not specify what type of method that you need to use, you have to identify yourself, analyze yourself. If all 4 temperature are given, of course you can use both method. Both also can. Okay. Of course, if you want to use the effectiveness, the mass flow rate has to be there. Otherwise, you will not able to calculate CH and CC. So you need to understand and then check all the information given before you decide which method to be used. But normally, if all four temperatures are given, just use LMTD method. Otherwise, you use the effectiveness NTU method. Okay, so as I mentioned just now, you have to know the relationship between the effectiveness and then the NTU, whereby it is equal to UAS per C mean, and then the capacity ratio C is equal to C mean over C max. Okay, and then you have all those chart to get either the NTU or effectiveness value. Okay. Any questions, students, before we go for the 10 minutes break? And then we can come back for this example. Hello, can you all hear me? Okay, so 10 minutes break, students. Hi, students. Shall we continue with the examples 11A? So to familiarize yourself with the effectiveness NTU method. Okay, so we read the questions. Are you all with me, students? Can I get some response from you all? So the number of attendees for today's class is not so good. It's only about 41 of you. Okay, all right. So I would like to continue. Okay, a counterflow double pipe heat exchanger is to heat water from 20 degrees C to 80 degrees C at a rate of 1.2 kilogram per second. The heating is to be accomplished by geothermal water available at 160 degrees C, meaning that that's the one, the geothermal water is the hot stream. Okay, used to heat the water, meaning that the water is a cold stream being heated up from 20 to 80 degrees C. Okay, and the heating is done by the hot stream by using geothermal water, and the TH in, the inlet of the hot water, is 160 degrees C at a mass flow rate of 2 kilogram per second. Okay, the inner tube is thin wall and has a diameter of 1.5 centimeter. The overall heat transfer coefficient is 640 watt per meter square per degree C. Okay, the U value is given. If it is not given, if the heat transfer coefficient hash value is given, then you have to calculate your own U. Okay, using the effectiveness NTU method, determine the length of the tube in order to achieve the desired heating. Okay, so the question says actually specify the method that you need to use. Otherwise, in fact, you can use LMTD. Why I say so is because of, you see, inlet and outlet temperature of the hot water is of the cold stream is given. Only the TH out is not given. By using the mass balance, I can easily get the TH out. But since the question is asking us to use the effectiveness NTU method, then we use this method. Okay, let us move to the whiteboard. Okay, so this is the one, okay, that I have read just now. All right, then as usual, you need to draw the picture, okay, to illustrate all the information given by the questions, and then easy for you to proceed with the calculations. Okay, it's always, okay, need to draw the picture. So this is counterflow double pipe again. Okay, so this drawing is belongs to double pipe. Okay, so it is doesn't matter. Okay, the um type of the float under the shell side or under the tube side is okay, no worry, because for double pipe it doesn't involve in any calculations on the flow, uh, whereby it goes into the shell or goes into tubes. Okay, so you can put it in the other way around also, no problem. TC in is equal to 20 degrees C, whereby this is a water. Okay, and then the mass flow rate given as the 1.2 kilogram per second, and then this is coal, and then CPC is equals to 4.18 kilojoule per kg second, degree C. Okay, the outlet temperature is given TC out here is equal to 80 degrees C, and then here the TH in is geothermal water. Okay, and the TH in is equals to 160 degrees C with the MH 2 kilogram per second, and CPH is equal to 4.13 kilojoule per kg degree C. Okay, and then we do not know TH out. Okay, the question is just asking you to determine the length of the heat exchanger. The L equals to how much? We are not needed to calculate TH out. but it is not given. So we will proceed to the effectiveness NTU method. As I mentioned just now, this one, in fact, you can use LMTD. You can use LMTD. From here, the energy balance, you can easily get the TH out, whereby Q equals to NC CPC TC out minus TC in. And also it is equals to M hash CP hash TH in minus TH out. All right. So here, once you calculate the Q from the crow side, because the TC out is given, then you can easily get the TH out, then proceed to LMTD method also can. Okay, also can. So right now we proceed with the effectiveness NTU method. Okay, students, you need to do there some analysis. The question is asking you to determine the L. Okay, I always encourage you all to call out the equation. Okay, it is equals to Q equals to divided by Q max. Okay, and then you have the NTU, isn't it? Effectiveness NTU, whereby it is UAS divided by C mean, right? Of course, you have the capacity ratio C mean divided by C max. Okay? In fact, from this relationship, I need to get the L, isn't it? Whereby this is equals to pi dL. Meaning that I need to get the NTU. How I calculate the NTU? Of course, I need to know the effectiveness, because the effectiveness is a function of NTU and capacity ratio. When I know the effectiveness, then I will know the NTU. Okay? So this is the way, the connection. Once I get the NTU, of course, this two, the relationship between effectiveness and NTU is based on the table or based on the chart that you might need to refer to later on. Okay? And then after that, C means you can get it easily. U is given over here. U equals to 640. Then you can easily get the L. Diameter also given over here, which is equals to 1.5 cm. Isn't it? This is the way how you do the analysis. Okay? So you can proceed. Always start with determine C mean. Then you will calculate CC, MC, CPC, which is equals to and then it is equals to then CH. This one always the very first step for the effectiveness NTU method. So if sometime you panic, do not know how to start with, this one always give a very good hints for you. So from here, DCC equals to C mean equals to 5.016 kilowatt per degree C. Don't forget, I need to get the NTU in order to get the L. So before I get the NTU, I need to get the effectiveness first. Otherwise, I couldn't get the NTU. Okay. So after that, you just need to do the calculations whereby effectiveness equals to Q over Q max. Okay. And then you can easily get the Q. Okay. So I will use MCCPC, TC out minus TC in, because maybe some of you will ask why I don't use M hash CP hash TH out, TH in minus TH out, because I do not know the TH out. I don't know. That's why I use the code stream to get my Q. Okay. So after that, it can be easily calculated. 80 minus 20, then you can get okay. Then Qmax also simple. Is equals to Cm, C mean, Th in minus Tc in. So C mean is this one. Th in is 160 minus Tc in is 20. Then you will get okay. I hope you all are following, students. Then eventually you will get the effectiveness. Okay. Everybody get the value 0.428 or not? 0.428 effectiveness. Are you all calculating? Students? Okay. So that's the way to calculate the effectiveness. 3 over 7. Better to put it in the normal number type. Yes, correct. Okay. Then we will proceed back to the whiteboard to continue with the calculations. Okay. So don't forget, if you want to get the NTU, there's a relationship between the NTU and the effectiveness. There must be the capacity ratio C over here. Sometime the student from here will straight away calculate the C, capacity ratio. Equals to C mean over C max, then it is equals to 5.016 divided by 8.62, and it is equals to 0.582. Okay, so you get your capacity ratio C. Okay, so from here, what will be the next? The next, of course, we need to get the NTU, isn't it? So to get the NTU, okay, this is what type. You can use either equation or chart, okay, or chart. Both also can, but equation will give you more accurate results, okay? Because the chart, the value from the chart is actually calculated from the equation, okay? All right, and then you need to check what type of heat exchanger is a counterflow double pipe. So counterflow double pipe, like this. So counterflow double pipe, you need to go back, okay, the chart or the table. So means that you can go, because you need to get the NTU, isn't it? By knowing the effectiveness, either you use this equation. So the C value, yes, is less than 1 because the C value that we got just now is 0.572. Sorry, 582. Okay. Either you can use chart. So counter flow, this one, chart B. So this is the one, chart B. Okay. So how to get the effectiveness NTU value? Effectiveness you already calculated, which is 0.428. Okay, so I go back to the slide first. Maybe slide first. Okay, so here easy for you to jot down anything that you would like to. Okay, so here it's a counter flow, isn't it? 0.428 is somewhere around here. And then your C value is around here, lumped together. So it's really, really difficult to check the value, but I know it's somewhere around here, the NTU. If it's this case, better you go and use equations. So it is counter flow and the C is less than 1. Can you do the calculation NTU by using these correlations? Students, can you proceed to the calculation? Just now C we determined is 0.582. Okay, then the effectiveness itself is equal to 0.428. Okay, can you substitute the value in it? Any one of you can give me the answer? Anyone? NTU value students? Yes, 0.651. Easily substitution, easy calculations. Okay, the answer for the NTU value is 0.651.